So basically, last time we talked about the work energy theorem, right? And we had, we'll go over some basics before we have our nice PowerPoint to talk about. Hold on. You have to click so many times with this thing. Okay. So while we're waiting for our nice thing to upload, but we talked about the work energy theorem. And before we could talk about work and energy, so we had work is equal to delta K. And I write that at the bottom because we have to look and refresh ourselves. What are these things we're even talking about, right? What are work and what are delta K? What's kinetic energy? So you'll remember we defined work as the so work is done by applying a force. When a force causes something to move a distance, we are said that that force does work, and that work is quantified as F dot D. And does anyone remember my question to see who's really on it, who's paying attention? Is this definition I've written down, is this general, or have we made a specific assumption here about the force? What do you think?
General. It's general, right?
It is not general. We've made a restrictive assumption about the force here. Do you know what assumption we've made about the force?
No, I don't.
This is true if the force is constant. Okay? So this only holds, and when we looked at the work energy theorem, what is true in general is that the work energy theorem is true in general, but we've only so far proved it for constant forces. And so what we're going to do by the end of the chapter, hopefully today, is prove very, very strongly that we're going to understand this we're going to be able to generalize to variable forces and show that the work energy theorem is true. But this gives us work for a constant force, and this is sort of the easiest one. You'll remember that F dot D is equal to F D cosine phi. All right, where phi is just going to be the arbitrary direction between the force and the distance vector. And we'll wait for our PowerPoints to load up to see examples of that, because I want to go through the old picture, sort of start there, and then build up to our two examples, because we're jumping right into examples. I did not forget about our sled example. But just coming after spring break, sort of rushing into the exam, and then, I just want to get us calmed down a little bit first. So you'll recall that this dot product, this is the angle between these two vectors, all right? And now, we've only looked at kinetic energy, is the only type of energy we've looked at. We've sort of implied that there are more types of energy, and there are, and we're gonna talk about that. But for now, we just introduce kinetic energy, and this is the energy associated with motion. It's equal to 1/2 mv squared. Okay, and one of the big ideas to connect here is that work has units of joules, and kinetic energy, well, actually all energy, delta K, energy also has units of joules. Man, making a J is hard with this pen thing I have. Like, a lot harder than I expected. Anyhow. So, when we look at that, our units of J, we can then see that work and is also an energy type of term. Now, if you're wondering, well, how do you get that these units are the same? Let's kind of take a look here at the units. Let's load them down so we can look at it. You'll notice we have here kilograms, right, from the mass. we have meters squared over seconds squared. Right. Yeah, you just got to get, it's 1 kilogram meter squared over second squared, not 1 kilogram meter per second. You got to be careful. So now let's look here at work, right? So we have a Newton, which is a kilogram meter per second squared, right? That's a Newton, F equals ma, times a distance in m, and we get, unsurprisingly, I hope, meter squared over second squared. So we can see from unit analysis that our two units are the same, and that should really, if it didn't before, I hope it really makes the very strong case that work and kinetic energy are the same type of quantity. They're both related to energy. All right. So does all this make sense? We're going to have pictures. If you want to see a picture example, that's exactly what we're doing next. So when I say we're going to move on to that, but stop and ask yourself if that makes some sense. Let me see. I've missed things in the chat. Oh, okay, I did not. All right. So let's get those files loaded up. Now everything is ready to go. So we want to jump right to, I wanted to jump right to here. So when I talk about that dot product for work, right? No, work is a scalar. All right, I just sort of lost my train of thought there. So work is equal to F dot D, right? Now, remember, we talked about evaluating the dot product is equal to the magnitude of F times the magnitude of D times cosine of the phi, the angle between them. So I want you to look at the picture here. All right? Now you'll notice that the D vector, they have this velocity vector, which is not helpful. But you have this displacement vector. So that's D. You can move, we can redraw the picture. That's the displacement vector, right? And we can draw the force vector like that. And we have this angle phi. And you'll notice that what I want to point out to you is that this is the angle between these vectors. It's not like constructing the triangle for components. Those are two different things. So you want to be careful. Basically, the lesson here in all this is don't automatically follow the math, right? You need to see when it applies. You know, if you're doing a dot product, you'll have some angle between those two vectors, and it will always be less than 180, right? It might have negatives and things like that, but you know, it'll you know, even if you, because you know, you can make there's ways to interpret this angle, right? If you go more than 180, say we do another vector, let's make it another color, right? Say you wanted to have this be your vector, and you said, well, gee, Professor Toland, now you have this phi here. I'd say no. That's not phi. This would be phi. That would be the angle between those two vectors. Okay? So I'm hoping that makes sense and you understand why 180 is sort of your maximum argument there. But we ended not in this, that's sort of the end of our review. We ended talking about the work done by gravity. Okay? So you'll notice we have our applied forces. And we talked about the work done lifting or lowering an object, applying an upwards force. We can also talk about it falling down. In the case we just talked about, it was going the positive direction, but in what I want to show you with the work done by gravity, yeah, in the thing we just drew, everything was positive, except that even that angle would have an absolute value. But when we look here, the negative sign will always come from the evaluation of that angle, right? If the angle is less than 90, you'll have a positive value. If the angle is greater than 90, you'll have a negative value. So the negative work doesn't come from the vectors themselves. It comes from the evaluation of that cosine phi term. Now, what we want to do is we want to understand work done by the force of gravity. So the force of gravity, as we can see here in these two, it's always pointing down, right? And we have an applied force, or a force that's applied always going up. But you'll notice that we can either lower, the displacement can either be, you can have something go up or down, all right? And when we have the displacement, if you're rising, you can, you can look there and you can see that the gravity will do, hold on, I need to get my pointers. You can see here that gravity does negative work if we're moving, if the displacement is upward. And that comes from, let's take a look at where that comes from again. That comes from that angle, right? So the work of gravity will be equal to, in this uppercase, Fg times the displacement times cosine of phi. Now, both these are positive because they're magnitudes, right? But the angle between f of g and d, if you look here, Fg is pointing down, d is pointing up. So that means that phi is equal to 180 degrees, right? So in that sense, gravity will do negative work, whereas this applied force will do positive work. And again, I know it says it on here, and you can sort of read that back to yourself, but you want to understand where that comes from, right? So the angle between the displacement and this applied force, in that case, phi is going to be 0. All right? So if we look here, we want to note that the work needs not be equal by these two forces. They are only equal if the initial and final kinetic energies are equal. If the works are unequal, you will need to know the difference between initial and final kinetic energy to solve for the work. So that's just telling you what you're going to need to know in order to solve these types of problems. And you have the opposite situation here, right, where the gravity can do positive work, but if you're falling in the same direction. And we have two, we want to look at the work done by gravity. We want to apply this to two examples, all right? So let's start with this example here. All right, so in this problem, we have an object that is pulled along a ramp, but the object starts and ends at rest. All right, so that's interesting. So if it starts and ends at rest, we know right away that delta K equals 0, right? And it even says it, no overall change in kinetic energy. It's explicit. Rarely are problems that explicit. So the rope will pull a 200-kilogram sleigh, which you may know, up a slope at an incline of 30 degrees through a distance of 20 meters. The sleigh and its contents have a total mass of 200 kilograms. All right, so the snowy slope is so slippery that we take it to be frictionless. How much work is done by each force acting on the sleigh? So let's take a look at the picture. So hopefully you were able to figure out the picture. Okay, so I want you to see if you can, if I asked you to do that, that was sort of the last thing I had you do before we stopped last time. We're now up to that point. So does anyone have any issue drawing the picture in figure A? Does that make sense? I'll go back to the problem so you can read it and see if you can come up with that picture. Just take a minute. I don't think it should take too long. Okay. So I'm guessing everyone could do it because I don't have any questions, which is okay. Now, the first thing to do is identify all the forces on the sleigh. So we'll do that here in a free body diagram. All right. And we're just going to recreate figure B. You'll notice we have gravity going down. We have a normal force. So we're on a ramp. It's one of these types of problems. So we'll have a normal force that's normal. And we will have a tension pulling us up the ramp. So we have tension, we have F normal, and we have FG. Okay? Now you'll notice what they did in part B, and those are the only forces, right? There's no friction. And you'll notice here we have the same free body diagram, so I'm actually going to clear what we have up there and start concentrating on this free body diagram. And you'll notice that they rotated the coordinates and made this x, right? And this normal vector here would be y along the normal force. And they broke f of g into its x and y components, all right? Now again, when you're breaking into components, you do have to create your triangle. We already went through it in a previous chapter, why you can call this angle theta. You can it is easy enough to conclude that this angle here is theta. I would implore you, if you don't believe me, to go back and either use your geometry or figure this out on your own. We did go over this several times in previous lectures as well. So that'll also be equal to theta. When you analyze your triangle, you get the x component will have a sine theta, and the y component will have a cosine theta. But now this should be pretty easy to do. So I'm going to go around. You'll notice we don't have much information. Like we were given things like we were given the mass, right? We were given the mass. We were given right? We were given a mass of 200 kilograms. We were given a D of 20 meters, I believe. And we have theta equals 30 degrees. So that's our given information. That's the stuff we have. And it doesn't look like a lot to figure out and sum the forces and get everything. I mean, I guess we could, but we want to know the work done by each force. So let's start off with the normal force. All right, so we have Fn is just Fn, right? And we don't want to write it that way because that's not what we're looking for. We're looking for delete, delete, delete. We indeed are looking for the work done by n, right? And that's going to equal Fn dot d and that's going to equal Fn d cosine phi. You'll notice I keep sticking with phi. So before we get crazy figuring out what Fn and d are, the first thing we always want to do is make sure that the angle is going to actually evaluate to something non-trivial. So when we look here, you'll notice that the angle between the distance, right? Because what's not written here is that this is our displacement vector, right? That's our d vector. And that is our normal force vector. We don't have to draw it on the free body diagram because there's a displacement vector on there. And we want to keep free body diagrams just for forces. So when we look there, we can see that f dot that phi is equal to 90, right? And so cosine of 90 is equal to 0. that implies that the work done by the normal force is equal to 0. Yeah, Nina.
So is it Fn we were looking for, or Fnx?
So,
Like, because we have it in an angle, right? If we were to analyze it.
well, remember, we don't have it at an angle because if you look at the coordinate system, we've rotated our coordinates.
Okay, so we're taking it. Okay, so we're taking as default coordinates as parallel to the angle, like the ground.
Right. So we've
Okay,
done the coordinates. I'm going to pick a different color here. We've done the coordinates so that I'll do green. Oh, I'll do a line too. Hold on. So you can see here. So that's going to be the y-axis, right?
Mm-hmm.
And then just so it's clear, that's going to be the x-axis. So that's going to be,
Got it.
yeah, that's going to be x, and that's going to be y. So in this coordinate system, there is no angle for the normal force, right?
Okay.
And we're looking for the work done by the normal force. So the question asks us, the question specifically asks us to find the work done by all the forces, and so I'm just going around picking one. So I picked normal first. So
Got it.
I looked at the normal force, and I have that the work done by the normal force, right, is equal to that force dot d. And even though I don't quite know what the normal force is, I first wanted to make sure that this wouldn't just go to 0, because I suspected it would. And lo and behold, because that angle is 90 degrees, it doesn't matter what Fn is, right? Because
Correct.
whatever it is times 0 is going to be 0.
0.
Now, the way to understand this physically is that the displacement is only along the x-axis. The sled doesn't hop up and down, right? It's not moving up and down and up and down. So mainly what I mean is it's not jumping like this, right, in that direction. So that tells us there's no distance in that direction, and we should sort of be able to see that there won't be any work done by forces in that direction. And we're going to similarly see, right, when we look at our next part, which is the work done by G. So we want to look for work done by G. There's two ways to do it, right? We can either look at the magnitude of G, Fg dot D equals Fg D cosine phi, or, and that's pretty easy to get, because if G is down here and is theta, right, and this is a 90-degree angle, theta, or hold on, bleh, theta plus 90 is equal to 120, right? So it's pretty valid to just look for M, to just look at this and write it as equals M, which we have, G D cosine 120. All right, that is a valid way to do the work, and as you can see, it's pretty simple. Another way to look at it is to look at these x and y components, and you can see right away that the x component, right, the x component here will be on the x-axis, and so that will do some work. And the y component, well, just like the normal forces in the y direction only, this part will do no work. So an equivalent way to look at this is to say that Fgx equals mg mg sine theta, where theta is 30, so that makes that easy. And then we can make the work is equal to Fgx times d, and that's easy, and then times cosine of 180, right? Because that's you'll notice that the x component here points down the ramp, and our displacement points up the ramp. So we know that the the force here does negative work, or gravity does negative work here, rather. All right? And you can look at that through the math. You can also look at it here, looking at the different directions. It should be pretty straightforward. Now, yes, Mina.
Sorry, I have a question on the definition we gave for the work based on the gravity, on the angle essentially. You wrote down cosine 120, right?
So I did cosine 120 here. These are two different ways.
I know but my worry is on the cosine, because I feel like we would get the wrong result if we didn't put minus 120
Nope.
for
You get
cosine.
cosine minus 120 will give you the wrong answer. All you care about, because remember, if you look, cosine 120 is negative. So you'll get the negative from taking cosine of 120. Do it in your calculator.
Got it.
Yeah.
Okay. All right. Thank you.
What your confusion is one that I think a lot of people are probably having and not talking about, though. So I do want to talk about it, which is the difference between a mathematical defined angle and that cosine phi. That 120 is just the angle. It's just the angle between those two vectors, right? It doesn't matter what axes you pick. It's always 120. And then a axis dependent.
Oh my God, you're right, because we are always selecting the angle that's the smallest between them. Okay.
Yeah.
Yes.
Yeah. So your components will depend on your choice of your axes, right? But the phi here is just, it's a relation between the vectors. It doesn't matter what axes you pick. Okay?
Got it. All right. Thank you so much.
I hope that makes sense, because that's a really, really key point to all of this. It's sort of the key to unlocking and making it very simple, as opposed to very confusing. Okay, so it's a really good question.
As long as we keep in mind always that when we do dot product, that's where the difference is. That's because the definition of the dot product states that we always select the smallest angle between the vectors, no matter what.
Right.
All right. Thank you, Professor.
And Fatima had a question? Let me go to the chat and see if it's there. Thought I saw a hand.
Hear me now?
Yes, I can hear you now.
Okay. Yeah, so the angle, it looks like the angle between the distance and the gravitational force is minus 120. But so we take only 120? We don't care about the sign? Is that your point?
So, yeah, so the displacement goes this, yeah. So that's, so yes, you only need the angle between them. You don't need the sign. You just care about what is the angle between those two vectors. That's it. Yeah. When it comes to the dot product.
Okay, thank you.
You're welcome.
Yes, but we can take 240 from the positive.
Don't do that.
To the gravitational force.
That's not the angle we'll take. We're always going to take, as Mina said, the smallest one. Okay.
Okay. Thank you.
No problem. This is a great thing to get clarification on. This is really important. So, okay. I mean, that's why we do these examples, right? So, anyway, now that we have our work due to gravity and our work due to our normal force, there's two ways to get the work done by the tension. So we can certainly use Newton's second law and solve for the tension and plug it into our definition for work. But in this specific case, there's a clever way to do this, right? That takes advantage of the fact that, as we saw in the beginning of the problem, delta K equals 0. Because that means that the work net equals 0. Okay? Now, 9 times out of 10, you're not going to have such a nice system, right? And you're going to need to find the force and do it. But in this particular case, because the net work is equal to 0, we can say that 0, right, is equal to the work of the normal force plus the work due to gravity plus the work due to the tension. All right, and we can just solve that and say we already know that one's 0. And we can say that the work due to the tension is going to be minus the work due to gravity. All right, and if you plug in the numbers, you should get, I think, about 19,500 joules. Does that sound about right? Someone plug in the numbers for WG. It should be negative, like 19,500, 19,600, something like that. Use those fancy calculators. All right, I'll use my fancy calculator. Come on, you guys can use your fancy calculators. All right. I looked it up because it's taking too long, and I am sad. It's taking too. It is 19. It's 19. It's 19,600 or work by gravity. No, that's too small, I think. Because I got minus, I was going to write it this way, 1.62 or 1.96. I don't know where, this is awful. My dysgraphia is not being helpful today. 96 times 10 to the 4th. That's what I have. Yeah. Okay, so right, minus, because remember that cosine of 120 is going to be negative. So that's what I get, and what we can see here is that the work done by the tension will actually be just opposite of the work done by gravity. So that would be minus 1.96 times 10 to the 4th is going to equal, plus 19,600, and that makes sense because the tension, right, moves in the same direction as the displacement. Okay, so does that make sense? Oh, good. Yeah, that could be bad. You always want to make sure you're in radian mode. So I think that's good enough. What I mean by that is, and I think I end up doing this too. I want you to sort of do this. We have another example with these with an elevator, but it's in the book, so I'm going to ask you to follow it. It'll be good to do, and it's just going over the same sort of stuff we did before. And this, the picture is very helpful. And again, remember, the real trick to this problem is when are you doing negative work and when are you doing positive work with gravity, and that will depend on whether you're falling or rising, right? Whether your displacement vector is down or up. Okay, and that's going to be the big part of that problem. So I'm going to pause it for about 10 seconds so you can stop and sort of work it out on your own. Right, so hold on. And then you can look at this part. And then we will go on to other things because I want to start talking about other things. And I'm noticing the time too. I didn't mind spending a lot of time on that example, but I think we got pretty much everything we can get out of it. And I think we'd just be rehashing the same stuff without any of the interesting angles that you can get from the sled example. So now we want to expand, right? So we made that assumption that F is constant. And now we're going to move on, right? So we're going to look at a spring force, which is a variable force. Now, when we look at a spring, we have to look at a mass attached to a spring sort of one of those famous physics setups, much like a block on a ramp, we have to notice three individual parts. We have rest, hold on. We have rest, stretched, and compressed. Okay? So basically, this position here is called the equilibrium position. All right? So if you're in equilibrium, if you were to hold this block, right? Say my pointer hand is holding the block, and I let it go, nothing would happen, right? Just nothing would happen. Now, if I stretch the block, say I move it back here, and I let it go, it's going to swing back and forth, right? And especially if this is a frictionless surface, it'll just go back and forth. Similarly, if I push the block, right, the spring force will be pushing it the other way, and it'll go back and forth. Now, I want you to notice something here. I want you to notice that the force is always in the opposite direction of the displacement, okay, for both of these. So when we look at this, there'll be some interesting things to see, but that's the first thing we should notice. Now, we're going to see that the value of the force, right? Because you can already sort of see that this is going to be variable, because what if instead of pulling the force out by this much, I only stretched it this much? It's going to go back and forth over a smaller sort of range, and the force will eventually be smaller. So we can see that the force that the spring can exert will be dependent on exactly how far I pull it back. All right? So we can already sort of get a physical sense of how the spring force is variable. But now we're going to get into it a little deeper. Okay? So the spring force law is given by Hooke's law, already indicates things we know. So we already saw that F is proportional to minus D, right? Or minus X. I'm not liking some of this this business here, where it's not for compressing it or transforming it correctly. So F is proportional to minus D, and we can see here that we'll introduce this concept of the spring constant. All right, the spring constant is a measure of the spring stiffness, and what it will give us is it'll change this proportionality into the equality we see here. All right, and you'll notice that here we have Fs is equal to minus D. Now, if we move that displacement along an x-axis, we can just write f of x of a spring equals minus kx. Now, this is interesting.
Professor, I don't know if you can hear us, but we lost audio.
Yeah, sorry about that. I got kicked out of the session by pushing a stupid button on my pen. So I can see we're still recording, so hopefully with people remaining here, all that worked. Yeah, sorry about that. So if we look here, now I'm like my great-grandmother. What was I saying? So if we look here, we can see something interesting with the fact that fx equals minus kx. All right, because I want to point out to you, without logging myself out, that remember, F still equals MA. And in this case will equal minus kx. That lets us do some interesting things. And what I want to point out to you is that you can actually, for the first time, we have sort of a simple physics equation, but hidden in this is sort of the really cool machinery of physics. Because what we have here is either, hold on, no, I want to clear this. Another way we can write Newton's second law is we can write m hold on. Oh, I'm like afraid of hitting the stupid button in this pen. Dt equals minus kx. And this is fascinating because what you have here, what we have here is a second order differential equation. And actually, this will be a second order homogeneous differential equation. And this is the language of physics, all right, or at least of classical mechanics. This is a much more powerful language than even calculus or algebra. And you're going to say, well, it looks a lot like calculus, and it does, but there are certain rules and procedures for following these types of equations. And this brings us to how we really express physics, which is pretty cool. Yeah, Mina.
I'm very sorry, but I have a question on the previous result we got. For some reason, I just don't get the result everybody else got. So I'm trying to figure out what exactly I'm doing wrong here.
All right. Well, so you mean before we got to forces?
Before the Hooke's law, maybe the previous one for the gravity. The last example we made for the gravitation force. Everybody found the result of 1.96 times 10 in the fourth.
Yeah.
Yeah, no, I have it in degrees. Nicholas, because
you want to be so the angles are given in degrees. So you want to be sure you're in degree mode. Not radian, right? And so you should be multiplying. So remember that you had mg, right, for gravity. Mm-hmm. is basically for the work you have Fg, which is m times g. Right? Mm-hmm. So that's going to be 200 times
minus 9.81
times 9, not minus because we're only doing magnitude. So times 9.81. All right, and then if you're looking at the x component only, you do have to multiply that by the sine of 30, and then you can do the other one, or you could just multiply that, right? If you do so 2 times 9.8, or almost 2,000 basically, right? And then you can multiply that by cosine of 120. That should, you have to multiply, to get the work, you have to multiply 2,000, right, by 20 kilometers, and then by the cosine of 120, and then you get the work. That should give you 19,600. So are those the four numbers you're multiplying?
Yeah, but I'm not getting the number.
You should. So 200 times 9.8 times 20, what do you get there?
39,240.
Now multiply that by cosine of 120. Because when I do it in my calculator, I keep getting 19,600.
Okay, hold on. 200 is the mass, right? Times
the
distance, 20, times 9.81, times cosine 120.
Yeah. I'm going to say if you don't get it, we'll have to talk about this over after class or something, like during office hours, because that's just going to be a calculator issue, because those numbers.
No, I got it.
You got it?
I think I know what I was doing wrong. Okay, got it. Thank you so much. Appreciate it.
You're welcome. But anyway, back to springs. So we can see that we start to get a little bit under the hood and more into what we're really, what physics really looks like, which I think is very cool. I mean, that's the type of stuff I get all excited about. So that being said, we can find the work now, right? And I don't like how they start it here. This is, again, not great. But what are you going to do? So work again can be positive or negative, and will depend on the net energy transfer. But let's take a look here at how we really start this. We don't start with just an integral. That is asinine. If f depends on x, right, we have to look at the change in work, right? A small amount of work is going to be equal to f dot a small amount of x. And why do we do this? We do this because any variable force, if you look at it in a small enough, if you break it down small enough, right, into a small enough portion, the force will look constant. There's reasons we start definitions like this. I don't know. This is something I have to change, I guess, when I go back and look at this stuff. This is not the correct. This is correct. It's not the correct starting place. Because, again, we're doing something physical, right? We want to make a hard problem that we might not know into something easy. And so the way to do this is to integrate both sides. When you integrate this side, for instance, you get the work. And if we take the integral of this side, we're left with this integral. Okay? Now, let's plug it in and see what we actually get here. All right? So we'll notice that when we get the work, it's going to be equal to the integral of minus kx. That's x initial, x final, dx. So that's a simple enough integral to do, right? We'll take out the minus k, and we have x squared final over 2 minus x squared initial over 2. And I'm hoping that looking at this step here, because again, you'll notice you have minus k out here, the algebra is simple, and you should be able to get this expression for work. Okay? So when we have a non-constant force, we have a more general description. Okay? Now, we haven't proved the work energy theorem yet, but we will. Now, again, let's take a look at the conditions for positive and negative work, because those are always the scariest. Oh, I guess I forgot. I'm still not here. Allow. I forgot to share the video. And we know that this will fix itself over time. So we now have our expression here. We want to look for the conditions for positive and negative work. The work is positive if the block ends up closer to the relaxed position or the equilibrium position. I like that word better than it was initially. It's negative if the block ends up farther away. So basically, you have to look back at our pictures, right? And you have to ask yourself, so I'll have some initial value, right? Say it's right here. In my final value, do I end up closer to the equilibrium position or farther away? Like off screen or somewhere like that. And that will determine whether you have done negative or positive work in your spring system. All right, from 2 points to the next. Okay. So if we take our initial position of 0, right? So let's write this down and get to the crux of the matter here. If we start from equilibrium, it's going to equal to 1/2 kxi squared minus 1/2. I'm not messing up the initial and the final. I mean, I know I mess up a lot, but if you remember, that comes from the math we did in the last slide. Since it's already got erased, I'm not going to do it again. I would suggest you rewind the video. And do that. But, sorry. So if we take our x initial, right, we'll call that xi equals to 0. We now have our work done by the spring is equal to minus 1/2 kx squared. All right. And so if there's an applied force where the initial and final kinetic energies are 0, that applied force will do a work that is opposite to that of the work done by the spring. All right. And again, it says down here, you know, if the block is attached to a spring is stationary before and after displacement, then the work done on it by the force to the applied force displacing it is negative of the work done on it by the spring force. It's just putting into words what we said here. So now we finally have a checkpoint. Good. I want you to do sort of an easier example. So we have 3 situations, the initial and final positions respectively, all right, along the x-axis for a block in 710. So that's just, let's redraw the figure. So we'll just say it's at the equilibrium point. You can compress it a little, or you can compress it a little, or you can stretch it a little. All right. And we want to know, we have these 3 situations, right? A, B, and C. In which situation is the work done by the spring force on the block positive, negative, or 0? So I will remind you that the work is equal to, again, we want to be careful. So this should be pretty simple. So I'll give you a little bit, and then I'll see if I'm not getting answers, I'll do the first one for you, and then I'll let you continue on to B and C. So, and I mean, we're going to go over it. Okay, so if you're struggling to see it, remember the trick here is you have initial and final positions. So this is always initial, and that's final, right? And the initial position here is 3, final position is 2. So let's just plug it in for A. We have 1/2 k, 3 times it's going to be 9 minus 1/2 k times 4, and that's going to be equal to 1/2 k times 9 minus 4. Well, they're not all going to be negative because I think we're getting this one to be positive. Squares are important. Squares are important. So let's see what you get for B and C, and then we'll go on break. So negative, positive, 0. I think we just found it was, the first one was positive, Fatima. So the next one will be, if we look here, we're going to start with 2, 4, minus 9. So that's going to essentially flip everything, and that will be negative. And then they're both going to, the squares, this will square away, and you'll have the same quantity, and that'll be 0. So I think positive, negative, 0 is going to be correct. Okay? So if you're still working through it, You can see the answers there. That's okay. Final. The point here is that, remember, the initial minus final comes from doing the calculus. There was a minus sign, and we absorb it in. So this is when you have to be careful of math versus physics, right? So it's about 2:08. We'll take a break till about 2:20. You only need K. You don't need K to figure out if it's positive or negative. If you want a numerical result, you need K. But just for figuring out whether it's positive or negative, it's just K. Yeah, it always has the same value. It's not changing. It's not dynamic. All right. I will be back in about 10 minutes, but like I said, we'll get started at around a little after 2:20, 2:21, 2:22. Okay? I'm back. Yes, Mina.
Hi, Professor, again. I'm
Hello.
sorry. I might be becoming a little bit tiring, but
No, it's fine.
I still insist on the previous, where I had a question on the previous one for the gravitational force.
Yeah.
Well, the result of the WG, right? The entire thing. The result answers essentially. No, so how I'm not sure how to put it. What was the question we needed to answer? Was it to find
the question we wanted to answer is how much work is done by each of the forces. So you have tension, gravity, and normal force.
Okay, perfect. So we know that the work from the tension is essentially the component on the x-axis of the gravitational force on the opposite side.
Yeah.
Is that correct?
Yeah.
However, the result we found, 1.9, so 19,000 something, is not the x component, is the entire thing.
No, it's the x you can do it both ways. So you can do it either just the x component, and then you have to do the whole thing times d times cosine 180, or you can do that's the x component. So you'd find that, or you can do the whole thing. So hold on, let me say that again because my blood sugar is a little weird. So if you do the component, right, you do the whole thing times you do f times d or mg d sine 30. That would be your x component, and then you multiply.
Let me do it while you're stating it. Okay, the final thing is, let me put it this way: it's 200, right, which is the mass.
Hold on, let me do it on the whiteboard because
yeah, sure.
this will be faster.
Because
So the two ways to do it, there's just two different ways to do it, right?
Yeah.
One is you can look at fx, which is equal to m fxg md mgd. I'm just going to put the g over here. mdg sine 30, and then you can calculate the work, which will be equal to mgd sine 30
times
right?
distance.
Distance is already I messed up. This shouldn't be there. Yeah. So mg mg sine 30 is the x component. mgd sine 30 is the work component. And then that will be times cosine of 180.
Okay.
All right.
All right. So let me do this. So I'm gonna calculate only the fx.
Yeah.
For a start. So it's 200, right? Times 9.81 times sine 30.
Yeah, you should get about 980.
981.
Fine.
Okay. Times, let me see.
Times, so now for the work, you have to multiply that by d.
Okay, by distance, which is essentially 20 meters, right?
Yeah. And then
that result will be multiplied by cosine 180.
Right, which is just -1. Got it?
Yeah.
Okay.
I don't know why I was getting the opposite.
I don't know either.
I'm so confused. I'm sorry, Professor. I feel like my brain is very well fried.
Well, I'm with you. I hear you, but it also means you're doing it right. So confusion is kind of what we do. In this so the important thing is to kind of work through it. If you'd like, the example is in your book, so you can go and sort of look at it and marinate with it for a little while. Okay?
Yes. All right. Thank you, Professor.
No problem. All right. Let's go back to our chapter. Okay. Hold on. I just need to get reacquainted here. All right. So now we're going to look at our variable forces, our general variable forces. And what we're going to try and do is, oh dear, it doesn't want to load a bunch, so let's just keep going. We're going to try and develop the work energy theorem and show that it's true in general. All right. Oh, see, I skipped it already. Okay. So we're going to look at work done by general variable forces. And now instead of being specific, we're going to get really general. Okay. So we're making no assumptions now about the force. And our goal is to show that the work energy theorem still holds. So to look at this general variable force, we want to take a one-dimensional example, because we can always extend to 3 dimensions without losing generality, right? And we can look at a function like f versus x, you'll see here. And if we look at our original integral, right, we'll have an idea that it's equal to, we already know that it's going to be equal to f dx, right? And so when we do that, we can look at the work itself as the area under the curve, because that's how we interpret Riemannian integrals, right? And this is very much a Riemannian integral. If you take enough math, you'll learn that there are indeed different types of integration. The type we learn in calculus is the Riemannian integral. So of course we have this area, but when we really think about it, we're breaking it up into smaller parts here, right? Little smaller chunks. And we can do that, and we can break it into delta x. Oh, this is C. We can break it up into small chunks, and then we can break, which approximates the area, and we can take the limit as delta x goes to 0, gets smaller and smaller, and that gives us the area. This is just a review of Calc 1 and Riemannian integration, right? So when we go there, we can sum our rectangles and look at, we can sort of look at the, we can express it this way, that the work each individual work will be some, the force, the average force along that delta x I, right? And then as we take the limit as delta x goes to 0, and of these, of these values of I here, then we get, just from calculus, that's our definition of the integral, and we get our work is equal to that. Now in 3 dimensions, we can generalize very easily. And what I want you to notice, it says the work kinetic energy theorem still applies, and it states this without proof. So I am not okay with that. I don't believe that. So what we want to do is look at the proof. All right. So let's start off with our definition of work. All right. Now remember, F always equals ma. So that's where this replacement comes from. All right. And if you remember A, and this is somewhat of the power of those differential equations I was telling you about, we can express A in 2 ways. Okay. Now, when we look here, I want to look at this one for example. We've just made the replacement of A equals dv dt. We don't lose any generality, but I want you to notice we've not specified anything about x, a, or t. It could depend on anything and be a function of anything, right? We've made no assumption about it. All right. And now, if we use the chain rule, we can rewrite dv dt as dv dx, dx dt, right? Because we're saying that v, or x, that v will be some sort of variable function on x. We can write it this way. So dv can vary with x, and x can vary with t. All right, and that's just, that's a pretty easy decomposition. But you'll notice in this term, and this, this step here is probably not obvious, this whole argumentation. we can replace that with V equals dV or dV dx dz. So I want to take away the circles and sort of look at it again. So here, like I said, this step here is probably not so straightforward. This is some pretty abstractifications of calculus, but I hope you can see it uses rules you know, and is pretty simple, right? And so all it does is allows us to write ma dx, which we can get pretty simply, right? It lets us make a replacement and write the whole thing here as mv dv. Okay, that's it. That's all we've done. And you'll notice that they do that here by doing what they tell you never to do in calculus, which is canceling out those dx's. Okay, so now we have a new integrand, and again, the limits of integration are arbitrary, but if we're integrating velocity, we'll have vi instead of vf. Okay, and now you'll notice that because we have this generalized velocity integral, when we take the integral up, we quite trivially, because it doesn't matter what the function is here, we're even if the velocity is a function, we're integrating with respect to the function. So that's a little hard to see because you're used to doing a much more simplified version of integration, but believe me, it holds. And what we get is that we have 1/2 mv final squared minus 1/2 mvi squared from the integral. And now we can see completely generally that we started off with work over here, and we end up here. You'll recall that this equals delta K. And we can see that in general, without making any assumptions, we've now earned the fact that the work kinetic energy theorem still applies with an exclamation point. Okay? And these things always feel better after you earn them than just taking them for granted. Because now, we'll look at the proof again. Now you have understanding. Okay? And it's a beautiful proof. It's worth taking a look at. I'm a fan. Okay. So now we want to go on to our final topic in chapter 7. It's not our final topic of the day, but we want to talk about power. You shouldn't, the answer, if you ever have to ask yourself, do you have to memorize something? The answer is always no, because you can always look things up. You should understand it though. And just understanding how to prove things like this is just useful in physics, right? It makes the connections. The more you understand things like that proof, the more you'll feel like it's an overwhelming amount to memorize, and the easier it'll all be. So I highly recommend it. Yeah, I don't know that any quiz question or test question will be popped off right from it, but I would say that it will make answering a lot of questions a lot easier if you understand that proof. But now we want to get to our final topic of our introduction to energy, which is power. All right. I haven't looked yet, but it looked to me like it was near 85%, maybe even higher. It was very high, very, very high. We'll talk about that. We can talk about that after class, though, because I talked about that at the beginning of class. The power is the time rate at which a force does work. All right. So essentially, power, and this will be average, will be equal to the work over delta T. Now I want you to notice there's no delta here in the W. Okay, there's no delta term. So work is already sort of this dynamic quantity, right? It's already it already itself is equal to delta K. So to have a delta would be a delta delta. That doesn't make sense. So the rate at which you do work is defined as the power. All right, and we can take that limit just like we always do to 0. Take the limit as delta T goes to 0, and we can get that power is the derivative of work with respect to T. Okay, so the SI unit for power is a watt or a joule per second. And when you look at your energy bill, your power bill, for example, you'll often see kilowatt hours, watts, and hours. So a watt, when you look at an electrical system, watts are important. If you ever built a computer, the power you draw is important. and work energy can be written as power times time. And again, the kilowatt hour is what you see there. Okay. Now, another thing we can do is we can solve for the instantaneous power, and we can get from work, right? So if we have this part, that power equals dW dt. Let's just take a look at this as it goes. That's going to equal F dot D, or we have too many D's here, so let's delete that. Let's call it X. And we have cosine phi. So, or, right. So we have work is equal to Fx cosine phi. So we have that here, and you'll notice when you take the derivative with respect to t, you'll have a, when you do that, so d omega or dw dt, that's going to be equal to d dt fx cosine phi, and we just apply the derivative to the x term here, and that's where you get to collect it into this term. You get your v, and for a constant force, that's why we're able to take the force out, you have power equals F dot V. Okay? So, let's do our checkpoint. Oh, right, the pen is limiting me. So a block moves with uniform circular motion because a cord tied to the block is anchored at the center of the circle. Is the power due to the force on the block from the cord positive, negative, or zero? All right, well, let's think about it for a second. So remember, we want to look at F dot V and phi. So if we're in circular motion, right, we've got a tension, and we know our force goes this way, right, because that's the way our acceleration goes. And our V is going to be tangential, right? So that's the V vector, that's the force vector. All right. So what do you think it's going to be? Good. Remember, it's possible for dot product to equal 0, even if these don't equal 0, because the angle, no matter how you do it, in any point in the circular motion, the angle between the force vector and the velocity vector will, by definition, always be 90 degrees. So in that sense, there is 0 power, or no work is being done there. All right? It's the power associated with that. All right, so let's go to, we're done with chapter 7. So we're going to move on to chapter 8. Chapter 8, things get a little more interesting. Okay, so in chapter 8, we're going to talk about potential energy and conservation of energy, and we're going to talk about how different systems, so we've talked about the work done by gravity and the work done by a spring. We're also going to talk about how those two objects can store energy. All right, so so first we want to define potential energy itself, which we'll do here. I'll clear it because I don't want to cross it out. But potential energy, which is often given by the symbol here, U, right? This is energy that can be associated with the configuration of a system of objects that exert forces on one another. So again, this word system comes up. I told you to be mindful of that word in the previous chapter. All right? So we have to be able to define a system. Now, you'll notice they're a little more clear down here, right? A system of objects may be the Earth and a bungee jumper. Gravitational potential energy will account for the kinetic energy increase during the fall. So that's energy stored by gravity. And elastic potential energy could account for the deceleration by the bungee cord. That's energy that can be stored in the spring. So we have here two forms of potential energy. Now, physics determines how potential energy is calculated to account for stored energy. And basically, this is a huge task in the field of physics. All right. Once you can define the energy of a system, you know everything about it. Everything is based on that. And this actually holds true for both classical mechanics and quantum physics. The first thing you start out with in any quantum mechanical system that you need to know is the total energy of the system. Once you have that, you're done. I mean, you're not done, but that's where you start using the machinery of quantum physics to make predictions. So it's a very important topic. It's a very important concept. All right. But here, of course, we're going to stick to mechanical energy. Now, for an object that's being raised or lowered, of course, raising and lowering is a simple system, the change in potential energy will be opposite the work. All right. So let's take a look at this here. So we have here our gravitational system and also our elastic system. Now, here, as the apple goes up, negative work. You know, let's be clear about this. It's not just talk over the. It could say negative work is done, but let's look here. As the apple goes up, right, the displacement vector is up, but f of g is down, right? So they're in opposite directions. So this is d, this is f of g, and the work is negative, right? So if the work is negative, then we should expect, the question we ask is, are we gaining or losing potential energy, right? Well, if we look here, if delta U is equal to negative work, and the work is negative, as we rise, right, as this apple goes higher and higher and higher, a negative times a negative is a positive, right? So even though the negative work, we'll have a decrease, or the work will, you know, when we negate the negative work, we'll have an increase in potential energy. And it's true, as you go higher, you increase your potential energy, or gravitational potential energy, right? Now, with the apple falling down, in that case, let's clear this stuff. In that case now, we have our displacement vector, d, and our force vector, fg. So now our work is positive. And you'll notice that as we do more positive work, we lose potential energy, right? Because the potential energy is the opposite, or the negation, of the work. All right? That's what that minus sign means. That means that as the work gets big, as the potential energy increases, the amount of work that you're able to do on the system gets smaller. As the potential energy decreases, the amount of work you're able to do becomes bigger. Okay? And the same thing can be seen for the block and spring system. So does everyone see what I'm talking about there? Does that make sense? Okay, good. All right. Okay, again, it's like, and that's okay, right? Again, it's just, you know, you have your relationship about energy stored. It's easier to sort of see gravity. I'm fumbling over my words here because I'm realizing that when I do the recording, the video doesn't come up in the recording. So I'm going to see if this works as far as recording the session goes. I'm going to actually stop sharing the file. I'm going to stop sharing and see if the video of me talking should just come up, right? Everyone sees that? So I'm hoping it's just me talking. So now what I want to do is sort of show you exactly how it works. So basically, the higher up an object is, right, as I raise an object, it will hit at a faster speed, right, if I let it go. So if I raise the height of an object, it'll have a faster speed when it hits my hand at the bottom here, right? This versus, say, that. And what we can see there, you'll remember, kinetic energy is related to speed. So the higher we go, the higher I am from the floor, right, which is my hand at this point, the more energy is stored by gravity. And what that means is that after I let it go, if I let it go from a greater height, there's more potential energy, gravitational potential energy, that can turn into kinetic energy. Therefore, at the bottom, I have larger kinetic energy the larger my height is. And I hope that helps, because when I'm in class, I forego the whole apple thing or going over the equation, and I just do this because I think it's a lot more helpful and instructive. And that's what's going on. You can see how the energy is stored and sort of play with it. So I would say play with things of varying heights and things like that. And hopefully that got on the video. Otherwise, you'll at least be able to hear what I said, and hopefully you'll be able to repeat the steps on your own if you need to see it again. But yeah, I just realized the video portion is not covered in this way. So let me get back to sharing the file. We'll go back to our slide. Okay. So hopefully that makes sense as we go through it. So some key points we want to talk about. These are really important to go over. All right. Remember what I said? We have this word system again. And the system consists of two or more objects, all right? So the system involves things that are interacting. And a force that acts between a particle in the system, or a force acts between a particle and the rest of the system. All right, so I think what's their point here? Okay. So I thought we were going to be talking about external versus internal. So forces can act between, so if we have a system, right, let's just make two bodies here. Forces can act between objects in the system, right? These things can interact through each other via a force. And also, if we have a system, right, let's clear that. Say we had a system of particles. We could then look at our interest particle and see how it interacts with the rest of the system. All right, so that's just a little visualization of what we're talking about. Now, when the configuration changes, that means as you rearrange this stuff here, all of these particles, right, the force does work changing kinetic energy to another form. And when the configuration change is reversed, the force reverses the energy transfer, doing work W2. So thus the kinetic energy of the system, you're calling tomato block, becomes potential energy and then kinetic energy again. So the point here is that you can have the configuration change and then change back and essentially change potential energy to kinetic energy and vice versa. And this will be very, very critical to understanding our energy conservation. But we're not quite there at the energy conservation point of it yet. So before we talk about it, some forces it may be tempting to think that all forces will be able to help store energy, but that's not true. Only the conservative forces for which what we talked about where they're reversible, right? Whereby we do a configuration to get to the first one and reverse the configuration, do an opposite work and get back the original configuration. That's called reversibility, right? So that's only true and when the force involved is conservative. And so the gravitational force and the spring force are two examples of those conservative forces. Otherwise, we could not speak of their potential energies, all right? Now, non-conservative forces are those in which this isn't true. So this is only true for conservative forces, but examples such as friction and drag, these are not conservative forces, all right? And in fact, kinetic energy of moving particles is transferred to heat by friction, and thermal energy cannot this is an important but subtle thing. I'm going to say it. Thermal energy cannot be recovered back into kinetic energy of the object via a friction force. Basically, what this is saying, a way to think of this, is that without adding something external, you don't expect to leave a cup of coffee sitting on to put it in your refrigerator, right? Because you can isolate it and have it all of a sudden be warm by random, right? You have to add something external. The coffee won't heat itself up. So you know, that's what that means. You can't recover that thermal energy back. We have to add an external force to heat something back up. So things like friction and drag, non-conservative. Gravitational, spring force, those are conservative forces. And what's going to be extremely important is that if we look at how, if non-conservative forces are involved, this is going to seem counterintuitive, because a lot of things we'll talk about, we're going to ignore friction so that we can look at conservative forces only. And when we do that, we're going to see that it doesn't matter how we get from A to B. Okay? You could go from, you know, if only conservative forces are acting, you could even add a third path where you go all around the slide, you know, do some stuff, stop for a while, and get to B. It doesn't matter. The path doesn't matter. Any choice of path between the points gives the same amount of work. Now, you might be wondering that this is counterintuitive because we always use friction in our everyday lives. So when we're trying to picture, for instance, real objects moving in real surfaces, it's not going to seem to really make sense with what we're thinking, what we're used to, because our everyday world has friction, right? And then things become harder. However, if we could blanket everything with ice, all our paths with ice, well, our problems would start to make a lot more sense. Now, again, it's easier to think in terms of just conservative or mechanical energy and then add in the heat later. And one thing we can often do is see how much energy we're losing to heat. And if we were doing our original energy conservation lab project, that's what you would be figuring out, is how much energy is lost to heat by measuring other types of energy in the system and figuring out how much you should have in the beginning of something, right, versus how much you have at the end. So you'll notice that two things. The first one was that we have the forces it doesn't matter what path we use to get from path 1 to path 2. And if we take a round trip, right, the work done on the particle is 0. Okay? So you'll notice that this is, these two start points are just what we've been talking about. So I'll let you read them, and they correspond to our discussions of these two figures. All right. Now, this is one of my favorite examples, because what we can see here is have a system, right, in which it would be really hard to use forces to figure out the velocity or the speed at B, right? It's going through this curved path, even without friction, right? This would be a hard problem. And so what we can see is that what we're going to see is that it's easier to it's going to be easier to solve a lot of these problems in terms of energy than in terms of forces. All right. Yeah. So when there's no conservative forces, we're not able. Oh, I need to go back to the chat. When there's no conservative forces, we are not able to estimate the potential energy. That's not exactly true. We just know we're not going to recover all of the energy at the end of the process, right? We're going to lose some to heat. And that'll make sense when we talk about conservation of energy. So we're not quite ready to solve a cool problem like this yet in terms of energy. But one of the big hints to seeing something like this where energy lets us solve problems that forces just won't is solving the work here, right? Computing F dot D, if just conservative forces are present, is still difficult, right? Because there's all sorts of, you know, there's the D's become very hard. You have to break it up and calculate a lot of stuff. It's not the F vector that's necessarily difficult, it's just the D vector. However, the gravity is the only force that comes into play. So what that means is that we need not look at the actual path. We can create a simpler path, right? One where 0 work is done to get to this point, and we can just do F dot D down here, and we can get the work done to get to this point by choosing an easy non-physical path than following the physical path the object takes. All right? So the calculation here is much easier, but this is some abstract thinking, right? It's not intuitive at all. You have to be able to ask yourself, what would the easiest path be to do a calculation, not what path does it actually take. You don't have to get locked into that. Okay. So let's do a checkpoint and sort of check and see where we are. So we have a figure here, right? It shows 3 paths connecting point A. Right? We've got point A. All right, to point B. And the work to go along each path is indicated. So on the basis of this information, or a single force does the indicated work on a particle moving along each path. So what we want to know is the force conservative or is it not conservative? So I want you to take a look. Now remember, in order for the criteria, I want to remind you, in case you don't remember and have it written down, the criteria is that the work along path A has to equal minus the work to path B, right? Meaning, oh wow, that's okay. Okay, so I'm echoing. Okay, hopefully that's better. The web, right? So we want to see if when we go, when we go from A to B, right? When we go from A to B, it should be the same energy to get back from B to A, right? But you'll notice we have 3 different paths, so you want to take a look at that. No audio? You can't hear me? I haven't said much. Yeah, no, we're at the checkpoint, so I'm waiting for you guys to solve it. Okay? Now, when you look here at this checkpoint, you want to go from the paths, right? So we want to follow each of these circular paths from A to B and then B to A. Now in one of these, it looks like in this path we have minus 60, and then when we go back to B, we have minus the result. So it looks like this is satisfied. Right? So far so good. But now we go here and it's 60 joules. But now when we go here, it's still 60 joules. So when we follow this other path, right? Yeah, 60 equals 60 means one of them ain't negative. So it looks like we do not have a conservative force here. Okay? I want you to play with the paths until you see it. All you have to do is follow around and see if your criteria is true, right? Which is that you do work. It takes a certain amount. That force does work to get from A to B, right? So it says it's minus 60 joules, and then the opposite amount of work to get back to the original configuration. Okay? So, no. All right, let's see where we are and how much further we want to go. Okay, I think we're in. All right, I think we're okay. Right, because there's, well, I don't know about variation's the right word, but because of the variation, because you can do, you can get back, once you're at, you can get to A, if it's path independent, it should be the same work to get from A to B one way or the other, right? One way has minus 60 joules, the other way has 60 joules. Both, it only takes 60 joules to get back, but you can't have different energies. So that tells us it's not conservative. Yes, the answer is not conservative. Yeah. Okay. So I think we're at a good point to move on. So we're not going to stop quite yet. We'll stop after the next checkpoint. I think that's a better place to stop. So in the general case, we can calculate work as, we have that integral for work, right? We have this guy here. Yep. So if you remember, we started out the chapter saying, hey, that work, that our change in potential energy, right, is equal to minus our work. So all we do to calculate potential energy in general is we just slap in work here, our integral into this definition, and that's where we get this side of the equation. All right, you'll notice we just have the negative sign here, that's the minus, and the integral is the work. All right, now using this to calculate gravitational potential energy relative to a reference configuration with a reference point at the y initial equals 0, you get u of y equals mgy. So let's take a look at this. All right, so for f equals mg, I always mess up a sign here somewhere, so you'll all be able to enjoy that. We want to integrate from y initial to y final, right? We want to look at, we're interested here in delta u. So it's going to be minus. And so that will be, we'll just plug in the force, mg, right? And that'll be dy. And again, the force is, we really do need that. We don't want to, we really do need that dot in there. Can't see? That's not good. Can everyone else see? I just want to be sure. Okay, I just want to be sure, because if you can't, even if you can't see Artin, I know it'll be on the video. So that's the important part. So yeah. So if we look here, if we just hash through it, we get minus mg times y final minus y initial. And we want to look here at force times dx. So an object, so here, I think, and this is so the minus sign I'm always sort of getting lost on is, I know that a minus sign comes out there. A minus sign either comes from a dot product that's been ignored here, or from just looking at FG and having it go minus to cancel out the minus here and make that a plus. And then this gives us mgy. Okay? So the gravitational potential energy associated with, yes, Mina, let me read this first and then I'll get to your question. The gravitational potential energy associated with a particle Earth system, so that depends only on the vertical position of the height of the particle relative to some reference position, y equals 0, not on the horizontal position. And that, again, is the idea of raising something higher and higher. Mina, what was your question?
Was not a question. I just I was thinking of sharing the way I'm dealing with the signs. Maybe it was helpful for somebody else. That's
Oh, sure, go for it.
the way I'm always thinking is like absorbing. And when I say absorbing, if we consider the minus you had about before, when we need to put it and expand it, essentially, I'm considering like, okay, so the factor that absorbs it, the M and D YF, for example, is positive. So if it absorbs it, becomes minus. But in the other case where mg times y initial has already a minus in front of it, when you try to absorb also the initial minus, then it becomes plus. I'm not sure if that helps you at all.
I'm not. I mean, when I look at the thing with the with the minuses, where they always make sense to me, they make sense physically, and we have a lot of minuses going on. So our big minus, for instance, right?
Yes.
Like is a change. So when we have delta U equals minus W, for instance, that one makes sense to me because as one thing changes, the other thing goes in the opposite direction, right? So it means one thing becomes bigger, the other becomes smaller. As one increases, the other one decreases. But it looks like my signage issue in this particular problem is we usually have this dot product, right? And this should be a vector. And here's my issue, and the book sort of goes over it. Is this should be a vector a vector dot product, right? So you should have a dot here, and I'm pretty sure that when we have a force, right, lifting something up, it's going opposite of work and it's 180, and that's where the negative is actually going to come from. But what I don't like is that if you read the book, because I wasn't sure how the book did it, they just put in minus FG and ignore the vector property of that integral. So I think your book is being sloppy, like very sloppy.
The thing is with the integral, the way they have it, is the dx is not a vector, it's only symbol, right?
But you see, this is exactly my point, is I'm telling you, I'm flat out telling you I don't care what the book says. Force is a vector. Dx is a vector. These need to be dotted. And vector integrals do exist, and we use them constantly throughout physics. That's what I'm trying to say. So you only get this integral when you take that dot product, right? You only get this non-vector integrand. So you can't have your cake and eat it too mathematically. I don't care who says it. You know, and this is rare form for me because I'm usually against the mathematicians. But you can't call this the magnitude and have it be negative. And that's essentially what they're doing when I'm looking at it. And I think I always get confused with this because I usually read the book, to try and figure out what asinine thing they might say. And this always comes up. Like when I'm actually reading this, I don't agree with it. And I think they need to. I think if they want to be consistent in their definition, you would have this come from some sort of dot product. You'd ask where is the work doing this? Because essentially what you're doing is first you're looking at a force moving something, right? It's either moving it up or down. And you can have changes, negative and positive changes in potential energy. That's no problem. But you're always going to look at, when you do energy problems, for instance, you're always going to write, when you're doing your homework, you're going to say, oh, UG equals MGH. And that's fine, that'll work when you start, but then you have to ask yourself, what's your delta U? Are you changing, right? And because usually you'll just start from there and end at 0, and you'll sort of get used to that directionality. But when you're defining stuff in terms of first principles like this, I am not cool with what they did. And I was hoping that they would make it clear, but they just slapped the negative in there, and that's not cool. That's not cool at all. They've assumed, they've made that vector integral, made some assumptions without talking about them. And they're not wrong, like the result isn't wrong, but the reason why it's and this happens, and I'll yell at you guys for doing this too. It's not enough to be right. Your reasoning has to be correct too. Here they get the right answer, but I don't think they do it in the right way. They just don't. So anyway,
I just want to add for the particular one here, the equation 8.5, for example, says the annotation they use is not, they don't show vectors.
I know,
Yeah, so
but
if
the
we
height,
do
but what
use them, yeah.
the only reason I'm being insistent here is because I'm feeling like I'm getting in the book says and I say, and I'm telling you the book will tell you force is a vector, and that position is a vector, right? So the only way you can write, the only way mathematically that you can write something like this is if you take that dot product. Unfortunately, I think you're just gonna have to trust me on that one. But if you don't believe me, you can look at every way we did this in chapter 7, where we always respected that dot product in chapter 7, right? In the only time we didn't, we would write it like this, is if we just assumed the force and dx were in the same direction, and the vector, the directionality was trivial, the dot product was trivial. But again, you can't call this a magnitude and and you can't integrate a vector, right, with respect to a scalar. Believe me when I tell you, it just doesn't, like, that's just doesn't work. It's asinine. And when you take more calculus, you will understand that I'm correct. So I'm sorry it's confusing, and I don't want to go on to it too much because now it's getting into like an advanced mathematical discussion. But so we can talk about it more over office hours or something like that. But yeah, they basically, I think they dropped the ball there. All right. So basically, the takeaway is that you can calculate your gravitational potential energy is equal to mgy. Okay? As you increase your height, you increase your potential energy. That is true. All right. So with springs, they do the same thing. And again, you'll notice they just plug in that minus kx. So we'll deal with it because, again, it'll give us the right answer, but I'm not 100% convinced that that's going to come from, like I said, that place. But fine, it's not. It's now causing more harm than it isn't. And when we do that, we get the correct, though, expression. Again, the negative sign will come from somewhere. Right now, they're just slapping it in and not explaining it. That's my problem, essentially. Delta U, or the potential energy for a spring, will equal, if you have this reference point at 0, will be 1/2 kx squared. Okay, so that's just calling this one 0. So we now have the potential energy for US. You'll often write like this. And UG, all right, and those will be the expressions you'll use pretty much for conservation of energy. So I think we'll leave the checkpoint till next time. It'll be a good place to start. We'll review these. We'll start by reviewing these and talking about these, and then starting with the checkpoint. I'll take attendance with the. I'll take the attendance with the. Thing here. I'm probably in trouble. Okay. So if that's it, I'm going to stop recording.